not in the slide mode.
It's not in the full screen slide mode, actually.
I understand. Yeah.
Yes, that's great. So thank you everyone for staying back. And now we have with us Professor Alok from NIT Patna. To give a brief introduction, Professor Alok did his PhD from Bose Institute, Kolkata. And he had a couple of postdoc positions in South Korea, France, as well as in Japan. And then he was a visiting scientist at IISER Kolkata. So Professor Alok is essentially very much connected with IISER Kolkata, yes. And currently he's a faculty in the physics department at NIT Patna. And his research interests are on the foundations of quantum mechanics, particularly quantum information, quantum cryptography, and quantum metrology. And so today he is going to give a talk on sharing non-locality by unbounded number of observers in an arbitrary input quantum network. So I'd like to welcome Professor Alok and start the presentation. Over to you, Alok.
Yeah, thank you, Dr. Radhakrishnan, for this kind introduction. And I would also like to thank the organizers, especially Professor Panikdai, for inviting me for giving this lecture. So I shall be discussing about the non-locality in quantum networks, and then I shall discuss about the sharing of this sharing of non-locality in this network. So this work is done with my 3 PhD students, Sneha Munshi, Rahul Kumar, and Samsundar Mahato. And 2 publications produced and 2 or 3. Well, this is the outline of my talk. So I shall be briefly discussing about the Bell non-locality, which is very well known to us. And then I shall move on to the bilocality scenario, which is a network. It's the simplest quantum network, which is the bilocal scenario. Then I shall discuss about this arbitrary n-local networks. And of course, I shall discuss about this arbitrary input scenario, which was not discussed before. And then and then how to characterize this kind of non-locality and what's the relation to the original Bell non-locality that I shall discuss. And finally, I shall discuss about the sharing of network non-locality by multiple observers. Well, let's start with the Bell non-locality, which is the simplest non-local scenario, which is the Bell CHSH scenario. And in that, I mean, it is quite clear that there are 2 parties, Alice and Bob, and let's discuss in terms of the quantum games like this. So let's consider there are 2 parties, Alice and Bob, and they're sharing a common state lambda in classical theories. And they're receiving, the Alice receiving inputs, 2 inputs, 1 and 2. And Bob is also receiving 2 inputs, 1 and 2. And they produce the outcome dichotomy, that's a ±1 or 0, 1 outcome. So the most important quantity in this experiment is that the joint probability distribution, that is PABXY. So in Bell scenario, we actually, Bell CHSH scenario, we consider 2 assumptions. That is, one is the known as realism, and another one is locality. And together we call it a local realism. But we consider or real models where we can fix the value of the of an outcome before measurement, or the value was predetermined, or you can simply say that if you measure it and you can get the particular outcome, and that is fixed by a hidden variable lambda. And the outcomes are independent of the observables and the outcomes of the other party. So using this local realism assumption, we can actually write these joint probability distributions in a particular form, which is called the factorizability function. But it says that you can see here that Q lambda is a distribution of lambda. We can take distribution of lambda instead of single lambda. And there's a PA x lambda. So it is actually the probability of getting a particular outcome A. It is independent of the Alice's or Bob's outcome, that is Bob's outcome B, Y. Inputs of Y. So this is the locality assumption, and similarly for the Bob. So that means Alice's outcome is independent of the Bob's outcome and observables, and similarly the Bob's outcome is independent of Alice's outcome and observables. So here, observables means is that whenever Alice gets input x equal to 1, she performs a measurement A1. And if HCC gets the input 2, she performs the measurement A2. And similarly for the y equal to 1, 2 corresponding to the two measurements of Bob, B1 and B2. So what we get is that finally in the local realist models or hidden variable model, that satisfies the local realism that we can factorize the joint theory. That's very quite well known. And we know that in quantum theory, that does not happen because this is not equivalent in quantum theory. So that actually factorizability condition is not true in quantum type of states and observables we are measuring. So this fact is known as the quantum non-locality, and this non-locality is very well captured through the CHSH inequality, which is the simplest Bell inequality that is proposed. So as I said that whenever Alice is receiving input A1, 1 and 2, she performs the measurements of A1 and A2, and Bob performs the measurement of B1 and B2. So if we write this algebraic expression, which is upper bounded by 2. It is shown that in quantum theory, there are observables and states exist. For that case, we can go up to the value of this beta 2 can go up to 2. So that is highlighting the inequality, CHSH inequality, that was based on the local realist models. So what we get is that we get means is that you produce your quantum theory. Alternatively, you can say in a different way, that is, if you want to reproduce your quantum theory by a classical local realist models, that is not possible. You have to assume a non-locality in the classical models. So what is the optimization conditions for that? That is when we can get to, that is Alice's choice has to be the mutually anti-commuting. That is A1, A2, the two observables, they have to be mutually anti-commuting. And Bob's choice also has to be mutually anti-commuting. And psi is a maximal impact step. It is known, and you can find in many textbooks and almost all the textbooks, you can find that these Qubit examples, that is A1 equal to sigma x, A2 equal to sigma j, B1 equal to sigma x plus sigma j by root 2, and B1 equal to sigma 2, and B2 equal to sigma x minus by root 2, and the state is a singlet state that will give you the value 2. But there's a twist in the tail, because in CHSS scenario, to optimize this inequality, beta 2, you don't need to consider the dimension of the Hilbert space. And that is the power of the Bell's theorem, because this is actually required for the device independent certificate. Because device independent certification requires to assume that the devices are uncharacterized and the dimension of the system is unknown. So whenever you want to use it for the cryptographic purposes, you have to show that is your inequality is optimized without assuming any quantum dimension. So I will give a very simple derivation of it. It's a new derivation and it was not there. You cannot find it anywhere except in my papers. Is that we use is for optimizing this CHSH inequality. I know this was done by this Chielson bound and Chielson, and you can find it in anywhere. Even if you go to the Wikipedia, you can get it. But I think this is also very interesting derivation of it, and you don't need to assume any dimension. Everything will be derived from the optimization conditions. So we use a sum of square approach, and where we consider that the value of this Bell expression, that's beta 2, is less than equal to delta. So delta is definitely the upper bound here. In order to showing these, we assume that there's a positive semi-definite operator, gamma 2, that is greater than equal to 0. So we cleverly, actually, gamma 2 is written in a particular form for a particular state psi, is psi 2q equal to minus beta 2q plus delta. So you can see, as I mentioned, that gamma 2 is a positive semi-definite operator. Whenever it is equal to 0, it will be optimized. So that means optimization condition is simply when gamma 2 equal to 0. Okay. So for our purpose, we suitably choose gamma 2 in this very particular form. Let me explain a little bit, because omega prime, omega double prime are actually positive numbers. So definitely they are positive. And M1, M2, they are actually the positive semi-definite operators. And these are the polynomial function of A1 and A1, A2, and B1, B2. So definitely this is a positive quantity. This M2 dagger M2 is also a positive quantity that gives us that gamma 2 is a positive quantity. Okay. So let us now define M1, M2. If we can define M1, M2, we actually fix the values of the omega prime and omega double prime. So let us, without loss of assume this can also be proved. I'm not going to that. So M1 psi can be written as a particular form, that is A1 plus A2 by omega prime psi AB equal to minus B1 psi AB. Similarly, M2 is also written. Now, if you put this M1, M2 here in this equation, is gamma 2, you can find that this the above equation gamma 2 Q that can be obtained. It's a very simple algebraic calculation if you do. Now here omega prime is defined in a very particular form, that is A1 plus A2 psi the L2 norm, which can be written this way. This 2 plus A1 is to anti-commuting of average of the anti-commuting, and similarly omega double prime can also be written in this form. Okay, if you put it, then you find that beta to Q, that is the Bell expression's value, can be in this specific form plus omega double prime. So from this relation, you can simply see that when I mentioned that gamma 2's value is always greater than equal to 0, so definitely to get the maximum value of beta 2, that's a Bell expression, you need to get this gamma 2 has to be 0. And this is the condition of optimization that will fix the state and observables. So then the maximum or optimal value of this Bell expression is maximum of omega and omega prime plus omega double prime. So already I defined omega prime, omega double prime. So let's just put it. So maximum of root over 2 plus A1, A2 anti-commuting average plus the 2 minus of this same point. So you can simply see that this can only be optimized. You just take a simple derivation. Consider 2 plus x plus 2 root over 2 minus x. You just take a simplest dv by x. The maximum is that this A1, A2 has to be mutually anti, and which yields the value 2. And from the optimization condition, I said that gamma 2 has to be 0, as omega prime cannot be 0 because they are the positive quantities. So then this M1 dagger M1 independently has to be 0, and M2 dagger M2 has to be independently equal to 0. That implies that M1 psi AB equal to 0 and M2 psi AB has to be 0. And that will give you, since we take this M1 psi equal to 0, and that means actually you will find that B1 has to be 1 plus A2 by root 2, because we found that omega prime's value will be root 2, because omega prime is 2 plus A1, A2. So when 2 is anti-common, similarly omega prime will also be root. So that gives you the Bob's observable will be A1 plus A2 by root, and B2 equal to A1 minus A2 by root. So we fix, and if you can simply check that B1, B2 are actually anti-commuting, given A1, A2 are anti-commuting. And that actually fixes the Bob's observable, Alice's observable. And with these conditions, I have not showed it, but you can also fix the entangled state, and it has to be a maximally entangled state. So what we obtain is that the optimization of the Bell inequality, optimization of the Bell inequality provides us 3 conditions, that is Alice's observables and Bob's observable has to be mutually anti-commuting, and the shared state between Alice and Bob has to be maximally entangled. And the whole derivation is done without assuming the dimension of the system, which is a very important point when you go for the device independent circuit. Derivation, let us check. Well, now I'm moving to the bilocality scenario, because I discussed this Bell-Sitch scenario, and any such, let me just mention once a comment about this SOS approach we derived. This SOS approach can be used for many symmetric inequalities, for the asymmetric kind of inequalities, whether it is applicable or not. That's a good question, and one may try. Well, let's go to the bilocality scenario, and which is a simplest non-trivial network. So you can see that you can simply say that this Bell scenario is also a network, but it's a simple trivial network because there are only 2 parties. And actually, the multi-party generalization is also possible. You can see that there's one source and there are many parties. For example, the GHZ states earlier. For example, GHZ state. So it is a source is emitting a GHZ state. So there are 3 parties: Alice, Bob, and Charlie. They can perform the measurements. So the main difference of this non-trivial network is that, let me just show you the picture. That I have 3 parties: Alice 1, Bob, and Alice 2. I deliberately did not choose Alice, Bob, and Charlie because I have to go for the multiple parties. So that's why Alice 1 and Alice 2 have taken. You can see here that in a multi-party, the straightforward generalization of the Bell scenario is a multi-party Bell scenario. In their case, there's only one source involved. That distributes the particles or systems to the many different parties. But here in the bilocality scenario, there are 2 sources. You see that there's a source S1 and S2. that emits the physical systems to the parties. For example, the source emits the physical system lambda, Alice 1 and Bob. Similarly, the source S2 emits the physical system to the Alice 2 and Bob. The important assumption here is that these S1 and S2, they are completely uncorrelated. So that actually constitutes the assumption of bilocality. That means if you consider that rho lambda 1, lambda 2, the joint distributions of these two systems, lambda 1 and lambda 2, then they are factorized. So in the bilocality scenario, there are two factorizability conditions we'll be assuming. One is the source factorization, when the source is factorized. And then definitely the local realism assumption I already mentioned, the factorizability assumptions of the CHSS scenario. The two different factorization will be used to derive a bilocality inequality. Because always we want in a quantum theory, we want to derive inequality because of the robustness. Try to find the optimal value is important for dependence. So here, as I mentioned regarding the bilocality CHSS scenario, the joint probability distributions, here we also have a joint probability distributions, which is for the tripartite scenario. So we have the P, A1, B, and A2. And given the A1, X1, Y, and X2. So X1 is the input of this Alice 1, X2 is the input of the Alice 2, and Bob is also getting input I. And for the time being, I am considering that all of them are receiving two inputs, 1 and 2, and producing the two outputs, dichotomic outputs, 0, 1. So we can write this tripartite joint probability distribution in this particular form. Here we use the two factorizability assumptions. The source is factorized here because the rho lambda 1 and rho lambda 2 is factorized. And then you can see this A1, X1, lambda 1. It's important, interesting, because you can see Alice's input, Alice's outcome is only dependent on the Alice's input and also the lambda 1. See, sharing with Bob. Similarly, the Alice 2, her outcome is also dependent on the X2 and her state lambda 2. But interestingly, the Bob's outcome is dependent on both lambda 1 and lambda 2. So that actually constitute the bilocality assumptions. Okay. So once we get the joint probability distributions, definitely we can calculate the any correlation function if you want. So A, B, AX1, B, Y, AX2 can be written in this way. To the notation, because there are many clumsy notations, I'll try to explain as far as possible. Well, in a 2010 and 2012 paper, this Brancia, Gisa, and Piranio, they formulated a very interesting form of inequality, which is called the bilocality inequality in this particular form. You can see this is a nonlinear inequality. It's not similar to the Bell scenario, Bell CHSS inequality. You see there's a modulus here and also the root. And this bilocality assumption, if you do, then actually it is very easy to get the bound of 2. So let's define these quantities inside. Okay, also the notations here. Here delta 2, it actually means that the subscript 2 is for the number of inputs. That is, we are getting the 2 inputs here, and superscript 2 party. 2 parties here, so that both of them are 2 here, but later it will be changed to M. So now this is the correlation quantity we consider J212. So J212 can be written in this form, that is A1 plus A2. These are the two Alice 1s observable, and these two A12 plus A22, these are the Alice 2s observable, and this B1 is the Bob's observable. And similarly, the B2 is here, only difference here is that it's taken minus. By using this, you can just take the modulus of it. So by considering the modulus, when you take the modulus of this J21, so you can see that it's mod A plus mod B plus mod C kind of things you can write. But we know this mod B1 because it's a dichotomic observable. Mod B1 is always less than or equal to 1. So we will get this less than or equal to 2 here. And it's then after that, it is very simple to just putting the values of plus minus 1, you can see. Experiment, that is the lambda 1, lambda 2 can be a classical variables that's satisfying local realism, that's satisfying this source independence. So we'll keep the source independence intact in quantum theory as well. So we consider the two sources S1 and S2, they are emitting two distinct quantum state, and we may also consider they are entangled state. Later, actually, we can prove it, that is whether they are entangled state or not. So there are two quantum states, rho A1B and rho BA2. That's rho A1B is shared between Alice 1 and Bob, and rho BA2 is shared between Bob and Alice. And we can actually prove that this, again, this quantum value will be 2 root 2. It's just a coincidence. There is no such relation between them. So 2 root 2, that's also the violating the bilocality inequalities, that is greater than or equals 2. So again, the observable is that observable is Alice 1 to be mutually anti-commuting. Observable of Alice 2 has to be mutually anti-commuting, but Bob's observable has to be the commuting one. We have actually derived, actually before us there is a derivation was all derivation was done by considering the 2 qubit systems. I mean the Alice and Bob, every Alice and Bob sharing a 2 qubit entangled set. But here we consider that without any dimension. So that is again important because this is the one step ahead to formulate a device independent formulations of the quantum network. Of course, there are many important things are there because these probabilities are not convex due to the source independence assumption. Well, you can find the choice when you said the choice is that A1, A2 are mutually anti-commuting and B1, B2 are commuting. It is very simple to get such a choice in the qubit system. So you can see simply you can just particular observables and you can you can also choose the entangled state, maximally entangled state between Alice 1 and Bob to Alice 2. You can get these two. But again, as I elaborately explained the sum of square approach, because this only can be done if you directly calculate this this optimization by from these equations. You have to consider this. People have already considered this 2 qubit entangled state. But here we profile again the dimension independent optimization. So that was this powerful sum of square approach helping us to get this optimal quantum. So again, we are using the sum of square approach. Again, here the same procedure will be followed. I am not going to the details of it. The same line arbiter. Consider a positive semi-definite. This is gamma 2 to gamma 2 means again. Once again, let me clarify the notations. Gamma 2 to whenever there's a subscript, it is for the number of inputs, and the superscript is the number of parties. So we can again write this gamma 2 by cleverly choosing it in this particular form. So when it is optimized condition is when gamma 2 quantum will be 0 for a particular state. So then we can fix the state and we fix the observables. So this is the form we can write it in this particular form. And there it was a omega prime and omega double prime. Here we took omega 1 and omega 2, and deliberately we have taken the root. Again, this omega and omega 2 are positives, and M2, M1, they are also the positive semi-definite operators with and all the Alice's of Alice 1 of and Alice 2. So here omega 1 is defined in this very particular form. There's omega 1 and omega 1. Okay, similarly for omega 2. With this, you can find it in my paper. The difference I will give soon. So what we find is that the optimal value is just a maximization of this particular quantity. That is root U1 under this one and root under this one, and the omega 1, omega 2 are given in this particular form. So it's simple algebraic calculation will provide you that. The most important part, once again, I want to mention here is that in this derivation, we have not considered any dimension of the system. So we actually derived, that is, what is the minimum dimension required for this optimization, and it was not there in the literature. So, yeah. So now let us go to the generalization of it. So before us, there's a bilocality scenario was generalized to n-locality scenario in many different topological structure. For example, the star networks, for example, the linear chain networks, and many other networks. Also, there are many works have been done in the open networks as well, closed network as well. So I'm mainly considering here the open networks. So in that case, you can see that is the Alice 1, Alice 2 was here in this bilocality scenario, but it can be generalized to the n-locality scenario where there are n number of parties and there's a one central party Bob, and there are n different sources are there, and we consider these are the uncorrelated. So that is simply the n-locality assumptions. That is means all the sources, n number of sources are uncorrelated, and Alice is performing 2 because they are receiving 2 inputs, and Bob is also receiving 2 inputs, and this is already known and people have characterized it. So I have already mentioned these things. That is, let me say once again then, That is, this n-locality scenario involves n sources emitting state to the many independent observers. You can see that it is the source emitting to Alice n to Bob, and similarly there are many sources are there. And once again, the most crucial assumption here is that the sources are independent of each other. And this inequality was proposed in 2017 paper, that is Anjali and Tavatuli et al. This included in JB papers. They proposed this n-locality inequality for two input scenarios. And this was the two inequalities, and this is very simple inequality because here are A1 plus A2s for the ones there, so they have extended to the n number of values. So the V1, V2, these are the same two observables of Bob's remain same. And it is actually straightforward to show that also give to, and that can also be derived by using our sum of square approach. What I did is that we consider the case of arbitrary input scenario. Because arbitrary input CHSS scenarios people have considered before. And this is, for example, the chain bell inequality, and there are many other inequalities they consider the arbitrary input scenario. But star network in the network scenario, that the arbitrary input scenario was not proposed. So you consider that every Alice in this network, there are n number of Alice. They receive, each of them receiving the m number of inputs, and Bob receiving the 2 to the power m minus 1 number of inputs. So every Alice number of inputs and produces the output to 0, 1, and Bob is the central party. He receives the 2 to the power m minus 1 number of inputs and produces the output, again the dichotomy 0, 1, 1. So now it will be a little complicated. Let me try to explain it as far as possible. So we actually defined, because we had earlier we had only 2 inputs for the Bob, but here Bob has a 2 to the power m minus 1 inputs. So we'll have a 2 to the power m minus 1 number of terms will be there. For example, m equal to 2, it will give you the earlier results. So we define this JMIN, which is the correlation. Let me explain this. M is for the number of inputs. I is the number of terms, the ith term of this terms of this, and n is the number of Alices that is in the star network. So that is to the power 1 by n, because we are considering n-locality scenario. If it is 2, you can just m equal to n equal to 2, you can get back your earlier results. So now we define this JMIN, that is expression, in a very particular way. So this is also a correlation you can see, because it's a kind of same correlations like this, A1 plus A2, but we have m number of inputs, so there will be m number of terms. So we took the minus 1 to the power yxki. This is very important because we have to fix this quantity, and this will be plus or minus. And that we will fix by using the encoding scheme of random access code. Of course, we are not playing the random access code game. We are just taking the random access code scheme to fix this particular value. So that's a plus or minus. This is the a particular expression for the ith expression of this delta mn, which is the expression we defined. That's we can say the non-local expression, which is that here delta mn. Once again, I want to mention m is for the number of inputs and n is for the number of parties. So we define this one, and we use some identities, because otherwise it is very hard to manage, because there are many sums, and you see that there's a two summations, x equal to 1 to m, and I equal to 1 to the power m minus 1. So there are 2 summation and 1 product. So what we can do is that we use this inequality to actually make it very little simpler, because this is summation of product less than equal to product in this delta m and l in a very particular, simpler form. This particular form without, and then we define this alpha mk. This quantity is alpha mk, and that will be the taken summation over m, and later product over will be taken the 1 by n, and then we will be taken the product of this n number of Alices k equal to 1 to m. Well, in order to fix it, we consider a random variable y delta, which is in between 0 and to the power m. So there's a 2 to the power m number of n bit string we have. So, for example, every y delta can be written in this form. This y x1 equal to 1 delta, x equal to 2 delta. Let me do an example. For example, y delta 0, 1, 0, 0. So then the first bit, that is y x1 delta equal to 0. Second bit, y x2 x1 equal to 2 delta equal to 1, and so on. But here we consider the half of this bit, because y delta equal to 2 to the power m number, but we take 2 to the power m minus 1. So we choose only those input string where first bit is 0, because it's a completely random. So 2 to the power m minus 1 will have a first bit 0, and 2 to the power m minus 1 will have a first bit 1. So we consider this one. So that will actually fix the values, because minus 1 to the power either 0 or 1 will appear. That will eventually fix the correlations. Of course, it is not very easy to follow in 10 minute, 15 minute talk, but I would look at my work. So the function, this is fix the value of, as I mentioned, that 1 or minus 1, and then you can actually fix the correlations. And as I mentioned, as you see that the xk is for the particular k, particular Alice. In the whole network, there are n number of Alice, k equal to 1 to n. So there's a particular Alice, we took this xk, but xk is actually this encoding scheme is same for every Alice. So then we can actually say that k dependence may not be there. So alpha m k equal to alpha m, we can write. So it was a little complicated to find that what is the value of this alpha m k, but we did it by using the Hadamard code and this thing. Find what this is this paper that this is derived this. So the I mentioned that for all k we have the same values. So then take the 1 to the power n and the product of this k equal to 1 to the power n. That simply returns us back this alpha m, which is the classical form. So in the what I derive is that, even if I forget the what I said earlier, because it's very hard to follow, that in a network with m number of inputs and n number of parties in this network, you'll find this is the values of the classical bound. Okay. So in quantum theory, what we do that we consider the quantum states for every sources, and then, for example, this Alice n is sharing a bomb. There are m number of n number of quantum states are there, and using this again this sum of square approach, we found that the quantum value will be 2 to the power m minus 1 into m, and which is greater than this alpha m. That's the classical form. So then all the observables. Interesting fact is that all the observables of Alice, every Alice, there's a m number of observables because they are receiving m number of inputs. So all the observable has to be mutually anti-commuting. Now comes the interesting part, because number of anti-commuting observables are fixed in a Hilbert space dimension. For example, in a qubit system, you have maximum three and mutually anti-commuting observables. So then what that leading us to say, that is, if you share the 2 qubit entangled state between Alice and Bob, then in such a case, you cannot get the optimal. It is the dimension of the system. For for every Alice, you need m number of mutually anti-commuting observables. In such a case, you have to find a suitable Hilbert space dimension for the local dimension, so that you can get at least m number of mutually anti-commuting observables. That gives us that you have to increase the dimension of the Hilbert space. So this means that this inequality cannot be optimized for the 2 qubit systems. You have to increase the dimension. And that is the improved sum of square approach was actually helpful to find this optimization, and then we can fix the dimension of the system. So what we found is that each Alice, each of the n Alices, there are n number of Alices are there, has to share the m by 2 number floor, m by 2 floor number of 2 qubit maximally entangled states. That means you can take the d-dimensional states and suitable d-dimensional states, but we found that even you don't need to take a d-dimensional state, you can take the tensor product of 2 to the power m by 2, the m by 2 number of, m by 2 pair of the entangled state, if you entangled state you share, that will also be enough. So state can be written in this particular form. But every Alice and Bob has to share this particular kind of entangled states. So here is the ratio of quantum and classical violation, because it was very hard to follow that this expression, that what is the value for the arbitrary m, and we showed that if you plot the ratio between classical and quantum values, you can find that it is actually saturates to the 1.25, yeah, and up to the 50. Well, now let me move that. This is one form of inequality we have proposed, but we can also take the similar other interesting form of inequalities that is actually motivated from the chain Bell inequality. Why it is? Because you see that in that case there are n number of parties in the star network again, but Alice is measuring the m number of inputs, but Bob is also receiving m number of inputs. Earlier it was 2 to the power m minus 1 number. So we have to change the inequalities. Why we change the inequalities? Because there are many such inequalities required depending upon the purpose. Because similarly, in the two-party Bell scenario also there are many different kinds of inequalities there for the different purposes. So this is another n-locality inequality that we are proposing here. Suitable expression once here, that is Fm equal to this tau m j, so jmi to the power 1 by m. So as I mentioned, here there will be m number of terms because there are m number of inputs for the Bob. And this is a form of inequality, form of expression we defined. And for this, xk is the for particular Alice, kth Alice. And then we find that this is the final observable, am plus 1k is nothing but minus a1k. And this is actually quite close to the the two-party chain Bell inequalities. So this value we derive, this value will be this the classical value. The n-local value will maximum value will be the 2m minus 2 of this expression. I'm not showing it because it's in this 2022 paper. What I find is that the Bell inequality was not optimized for any arbitrary dimension before, and it was only the 2 qubit. Of course, it is optimized for the 2 qubit, but no one has tried for the arbitrary dimensions that we have also provided in this paper. So using this SOS approach again, we find that this optimal value of this Bell expression, n-local expression, can be written in this particular form. And then it is there. I'm not going to discuss. And the quantum value is 2m into cos pi by 2m. Well, then we can also propose different one, because we just reverse the role. For example, we take the Alice one is measuring this 2 to the power m minus 1, and Bob is measuring m. It may be, you may say it's what new you can get it from here. For example, in the scenario, for example, Alice is measuring m1 number of observable, Alice 2 is measuring m2 number of observable. To just reverse the role, m2 Alice measuring m2 number, m1 number observable. Sorry, Alice measuring m2 number observable, Bob measuring m1 number observable. Nothing have changed because the whole correlation remains same. But this is not true here, because here Bob is receiving all the systems from the n number of Alices. If you change swap the inputs, that is, for example, here earlier we have taken Alice 1 is getting m number of inputs, but here we are saying that Alice 1 is getting 2 to the power m minus 1 number of inputs, and the problem becomes really non-trivial and it's very difficult to optimize. Well, we found that the classical value of the expression, again, this is m minus 1 dt. I'm not going to detail derivation. But what I want to say is that in that case, using again SOS approach, we find that the relations between Alice is observable. That has to be m minus 4p by m, and that p also can also be fixed by the random access code. The important thing we get is that Bob's observable, when n equal to odd, they have to anti-commuting. When n equal to even, they have to commute. When n equal to even are commuting, that can be used for many interesting purposes. First of all, when n equal to odd, it's a mutually anti-commuting. So you can actually certify from the optimal quantum value, you can certify the set of mutually anti-commuting observables and the entangled states that is required again for the device independent certifications. And when n equal to even, that's become more interesting, because certification of commuting observable is very difficult to get. We know that is commuting observable. Normally, commonly they don't keep the violation and the CHSS scenario. So certification of commuting observables was not that easy. So we find that when n equal to even, you can actually certify the commuting observable as well. And not only that, when you have a set of commuting observable, that can be made to a protocol so that you can actually certify the entanglement, certify the entangled measurements. So this work is also submitted to now New Journal of Physics, and it will be appearing soon in the archive or in the journal. So, Dr. Alok, how much time I have? Because I forgot when I started.
You have around 15 minutes.
15
because
minutes.
you started 5 to 10 minutes late, and you have 10 more minutes. Yeah, 10 minutes late, and you already have 10 minutes, so you can go for 20 minutes. Yeah.
So now I would like to say that what's the difference between what is the correspondence between this Bell CHSH and Bell nonlocality and the network nonlocality. That's an interesting paper in 2017 by Nicholas Gisa and et al. They showed very interesting result, because this is the same bilocality scenario I defined here. They showed that this bilocality, this bilocality expression for quantum theory can be written as a CHSH of Alice and Bob, Alice 1 and Bob, and CHSH of Alice 2 and Bob. That means it is as if the product of two Bell inequalities, CHSH inequalities. Because it's a two input scenario, because you can see that Bob's observables are actually two parties are coming from Alice 1 and Alice 2. So in such a case, you can see that's a quantum theory, it's just a tensor product of two observables. This one. The result can be summarized in this from the following manner. That is, if rho A1B, that means this entangled state violates this independently, the Bell CHSH inequality between Alice 1 and Bob, and psi BA2, that's entangled state, that is that leads us a violation between Bob and Alice 2, then we can get a violation of the n-locality, bilocal inequalities. Right? So rho A1B tensor product rho BA2, they violate the bilocality. But their proof was based on this Perez-Horikoshi criteria, which is valid only for the two qubit entangled states. And it was generalization is also done, again using this Perez-Horikoshi criteria by this Devashish Sarkar in Calcutta University group. But we derived their result without assuming the dimension of the inverse, because we have this elegant sum of square approach. We go on network non-locality or arbitrary scenario. What I found is that, again, once again, I would like to say that's a BI. For every I, you have a BI, and then it can be written as a tensor product of this, because you are receiving in quantum theory, because Bob is receiving the states from this source. That's a n number of n number of sources are there. So Bob is receiving n number of physical systems from the n number of sources. So you can write in just a tensor product structure. So we actually write in this relevant Bell inequality, which is can be found in this Rubik Horizon paper. Here was also Isaac Kolkata BSMS students, published in 2019. So this Bell inequality is proposed, and we can show that we can write here Alice N and Bob is actually performing a Bell type measurement, Bell CHSH type inequalities, and this inequality is this one. And then you can say independently, that's a n number of Alice performing the Bell CHSH type inequalities with the Bob. And then there's a, you can see the I equal to 1 to the n minus 1 number of these terms. And we find that if this violates the Bell inequality between Alice N and Bob, and similarly for each of them, then actually the n-locality inequality can be violated. So this is the result we have. And similarly, the similar correspondence happen for this chain Bell inequality as well. So let me mention one more important thing is that it is as if that all the network inequality considered here can be traced back to a Bell type inequality. Which inequality is violated, then you can then network inequality will be violated. But recently, there's a work in the PRL in 2021 by this Kawakuli, Jisa, and Brandseer. They showed that they formulated interesting bilocality inequalities that cannot be traced back to the CHSH type of inequality. So this is a genuine inequality. And also, there are a few more works have been done along that direction. So we have also formulated another such kind of equivalent network inequalities which cannot be traced back to any known form of Bell CHSH, Bell type inequalities. So that will be presented elsewhere. Moving to the part of sharing. The sharing network non-locality by multiple observers. So sharing of the various type of correlations have been starting for a first one decade, and most one is the sharing of non-locality in the Bell CHSH scenario. And this is a paper that is published by again this Professor group in 2014, I think. 14. They showed that let Alice and Bob, there are two parties, they are sharing an entangled state. So if there are many sequential bobs you have, so how long you can get the quantum violation of
Hello.
I was disconnected.
Okay. You got this. I was just checking out if I got disconnected.
No, I was disconnected. Okay. So as I was saying, I don't know where I stopped. I was disconnected, but let me start again. That is, what we want to show is that let Alice and Bob are violating a Bell inequalities. So now we want to say that how long, let's fix Alice's observables are always there. Alice is not sharing anything. Bob, how many Bob can share sequentially the quantum correlation? That means by violating the Bell inequality, right? There are many Bobs, Bob 1, Bob 2, Bob 3, they're sharing the correlations, but they have to violate the Bell inequality. It can be shown that after some point, Bob 1 and Bob 2, they can violate Bell inequality. For example, of course, violation will be less, but in the Bob 3, you cannot get the violations. And of course, the important fact we have to mention here. If Bob 1 perform the sharp measurement, definitely disturb the entanglement fully. So in that case, there is no correlation remains for the Bob 2 to be shared or to be violating any Bell type inequality. So most important fact in this sharing is that you have to perform APOV or unsharp measurements. So if Bob 1 perform unsharp measurements, and it is so unsharp that it is just violate the Bell inequality, and you can leave the state for the Bob 2. In such a case, you can get actually then Bob 2 can also access some partially, less because the entanglement content. In such a case, he can also violate the Bell inequality. Then he can extract that information and leave the state for the Bob 3. Whether he can also violate Bell inequality. It is found that maximum 2 Bob can be able to violate the CHSH inequality. But there are many other types of quantum correlation have been demonstrated. For example, the coherence, steering, preparation contextuality we have shown in 2019 paper. So here I would like to share the would like to mention about the sharing of non-locality in a bilocal network and the n-local network. So the pictures, the figures remains almost same. That is, there is a Bob, the central party, Alice 1 and Alice 2 are here, and considering the sharing in the both the end. For example, Alice 1 is sharing with the kth number of Alice 2s are. Of course, except the final Alice, in intermediate Alices, they will perform the unsharp measurement. Otherwise, the system will be collapses to the system will become completely mixed. There will not be any residual entanglement left. So the unsharp joint POVM can be written in this particular form. For example, you see that I have not done anything to the Bob I tensor product identity because Bob is receiving two system. That is this I for the system S1 coming from S1, this I identity coming from the system S2, and this EXA, which is the POVM for the Alice 1, and EZC is the POVM of this one. So in such a case, the Gauss operator can be written in this form because it's a measurement operator that already Kumar mentioned. You have seen that. And then with POVM can be written in standard formulation. So here, particularly, I am considering the unbiased spin POVMs for each Alices. So you can say that Alice XZ for the Alice 1, AZ for the Alice 2. In such a case, you can write this particular this kind of POVMs. Where lambda 2k is for the 2 is for the here for the bilocality scenario, and k is for the arbitrary k in the Alice and both Alices L1 and Alice 2 spot. So the lambda is the unsharpness parameter whose value will be within the 0 and 1. Now we can from here we can actually define this the measurement operator, which is Gauss operator, which is m xz plus minus, can be written in this form. As I already mentioned, this unsharpness of this parameter is bounded by 0 and 1. When it is 0, there is no measurement actually. It is a completely unsharp 0. When lambda is equal to 1, it's for a sharp measurement. So now, as I mentioned here, after the after this Alice 1 and Alice 2, first Alice 1 and first Alice 2, they perform the answer measurement. The state left for the second set of observers will be the row 2 ABC, and this can be calculated in this way. And for the kth one, you can also calculate in this way. So for our purpose, we define this, we take the joint Gauss operator in this particular form. This is just a simple mathematics we did, and it can be written this. I mean, this measurement operator is written in terms of this identity and the observable A, and with the parameter gamma and delta. Okay, the gamma and delta are written here. And this is the explicit expression of the how to calculate this for the kth sequence of the Alices. Now, what result we get is that we calculate the bilocality inequality as I mentioned before. With the bilocality inequality, there's two terms, mod ik plus mod jk. That's I defined it before. You can remember. And then this gives a very particular this kind of form, and that is calculated. It's straightforward, but some laborious calculation you have to do. Now, coming to the result, what we found is that the critical value of Alice 1 left hand side, Alice 2 right hand side, the first set of Alice 1 and Alice 2, that they need a value of 1 by root. That means it is roughly 0.707. So lambda's value is limited to 0 to 1. So you actually exhausted 0.707. That means below 0.707, you will not get any violation. The second set of observers, you get 0.82. And for the third set, you get 0.16. That means that this 1.6 is not a legitimate value because, as I mentioned, the unsharpness parameter is limited to 0 to 1. So if it's beyond 0 or beyond 1, that will not be considered because it's not a legitimate value. So what we found is that in the bilocality scenario, the symmetric case of sharing, for example, how many Alice 1 is sharing, Bob also how many Alice 2 are also sharing. In such a case, maximum 2 sequential Bob can share the non-locality in the bilocal network. Now we consider the asymmetric case. Let's fix one Alice here, Alice 1, and let's consider how many Alice 2 can share non-locality. And for this, you have to do this simple mathematics, and then you can get that. If you keep this, you keep this one performing a sharp measurement, Bob performing sharp measurement, but Alice 2 is performing unsharp measurement. So how many Alice 2 in sequence can violate the bilocality inequality? There are 6 sequential Alice 1 can share the non-locality in the bilocal network. And that can be extended to our arbitrary n-locality scenarios. And we consider first the n-local scenario with 2 inputs only. And this is the inequality that we can define. And then again, everything remains same. But we found that again, in this case also, at most 2 sequential observers in every direction in the symmetric scenario can share the non-locality. But if you now want to share only one Alice's, and let's keep the other Alice's fixed. There's no sharing only one observer sequentially. In such a case, when n equal to 2, we got already that is result is 6 Alice's can share the non-locality. But sorry, 1, 2, 3, 4, 5, 6. Yes, but here for when you take the one part you increase n equal to 3. In such a case, the sharing actually number of Alices can share the non-locality can increase, and this is analytically proved that actually we can share arbitrary number of Alices can share the non-locality. That is proved that there's exist n, that's function of k, for which the non-locality can be shared across one edge of the star network. And as n is unbounded, so you can include many different parties. So then your sharing number of Bob can share numbers can share non-locality is also unlimited. So unbounded number of observers can share the non-locality in the 2 input scenarios. Let's generalize for the arbitrary input scenarios. We got the almost similar results, and this is the some results that I can show you the general results. So this is the general results we found. That is, in such a case also, in the arbitrary m input scenario, there are n number of parties. So you can find a number of m and number of m and n, for which the non-locality in the star network for the arbitrary input scenario can also be demonstrated for arbitrary many number of observers. Of course, there are differences between them because in such a case, when the arbitrary input scenario, you need the larger number of parties than. So this is the result I just see here. So I am running out of time. So let me just summarize it. So what I discussed is the bilocality and n-locality scenarios in quantum network, and we provide some non-trivial generalizations because we took the arbitrary m input scenario and we provide 3 such inequalities for the arbitrary m input scenarios. And all the optimization of these network inequalities are done without assuming the dimension of the system, and without assuming the dimension is very important because this is required for the device independent certification scenarios. And of course, later we characterize our network non-locality with the Bell non-locality. In fact, we showed that how there the correspondence between the Bell non-locality and network non-locality. And finally, I discussed arbitrary of the symmetric scenario. And with this, I would like to thank you very much for your kind attention.
Thank you, Dr. Alok, for your very interesting and engaging talk. Now, I'd like to ask the participants if they have any questions. So
I think this was maybe for the students. I believe so. I didn't know that this is a lecture I have to give. I could have given a different. Okay, no problem.
There is a question, but it's on the chat box. Can PT symmetric concept be proved through Bell inequality?
Yeah, it's a question whether it is related to the Bell inequality or not. Of course, the PT symmetric concept can be proven through Bell inequality or not. Yeah, I mean, it is not related to this one, but still, let me answer if I can. That PT symmetric Hamiltonian, people have PT symmetric measurement, people have concept. The problem is that in the PT symmetric case, you may get the violation more than 2 because in the PT symmetry, it is a non-Hermitian system. So actually, there is some confusion about it because it gives a violation to root 2. That means it can give the signaling as well. Because PT symmetric Hamiltonian, if you apply to the entangled system, that can lead the signaling. Because signaling is of course pseudo, because there is some problem. Because actually, this comes only when you consider the hybrid structure of the PT symmetry. PT symmetry Hamiltonian, if you keep in the non-Hermitian system, it's okay. Because now, if you apply the Hermitian quantum theory and the PT symmetric Hamiltonian, there is some mismatch between these two. But of course, it can be applied to Bell scenario, but you have to revise your motion a little bit. Otherwise, it cannot be applied.
So I hope it answers the question.
That's not proper answer, but maybe he can get some idea.
Yeah, I hope you got the answer. Yeah. Okay, if there are no further questions, let us all thank Professor Alok for his wonderful lecture. And thank you for your time, Alok. And
okay, bye.
Bye. I'd also like to thank the organizers for asking me out to moderate this session, and particularly Professor Prashanta Panigrahi. Thank you, sir.
Okay, bye.
And is anybody there from the organizers, like organizing committee members? Yeah. So this session is over, right? So the next session is at 3. Okay. Thank you. Bye.